Athar, can you see my screen? Okay. Okay, so we start for today. So, so today we will discuss about the critical result shear stress related problems and the forces on the uh, forces resulting from the interaction of the dislocations. So, have you gone through the lecture videos? Can you hear me? Okay. So I will just explain what is the that's shear stress on for a specific plane. So okay. So the in any crystal or material, we have some specific slip planes or slip directions in which we have the resolved shear stress required to slip in that direction. So when like this is a cylindrical crystal, so in this we are applying a tensile stress in this direction, sigma. So for this tensile stress and on this plane, on this crystal. there is some specific plane in which deformation will start first. So for that plane, uh, we calculate the resolved shear stress on that plane to calculate the required shear stress for the deformation. So we know that crystallographic plane have some Miller indices plane and the slip direction also. So this is the 111 plane, and so we define the slip normal for this plane. This is the slip normal. So slip normal Miller indices will be square. So because we are representing direction for this plane and slip direction. So this is the slip normal. Slip plane normal, and the slip direction will be on the plane. This. So this is the slip direction. So for 111 plane, the 1 bar 1 0 is the direction for the slip to occur, means glide direction. So for this plane, because the slip plane normal have some angle with the tensile stress axis, so we can define it as phi, and the angle between slip direction and the axis we can write as lambda. So the area of the plane will be, because the this cross section area is A, so area of the plane will be A by cos. uh, it's okay that we can you can manage. So I will explain it properly so that you understand what I want to discuss in regarding the problem. Okay, so area of the plane can be written as A by cos phi, and the stress on that in the slip direction can be written as, so, force. Slip direction will be mm, F cos lambda. So when if we want to calculate the stress, so stress will be F by area. So this will be F cos lambda A by cos phi. So F by A we can write as sigma. So this is the shear stress. Tau will be sigma cos lambda and cos phi. So this is the resolved shear stress we got for this 111 plane. So this is called as resolved shear stress. So, for materials like BCC, FCC crystal having different crystal structures, the slip direction and slip planes will vary according to the highest atomic density planes and directions. So, for those planes, the resolved shear stress value will be different. So, for deformation to occur, this resolved shear stress should exceed some critical value. So that critical value we say as the critical resolved shear stress. Uh, we write it as CRSS. So this is the critical amount of the shear stress required for the deformation. So if the applying force exceeds the resolved shear stress greater than this CRSS, then the deformation of that crystal will occur. So this quantity also means sigma is different and tau is both are stress values. Then the cos lambda and cos phi we say it as the Schmidt factor. So the Schmidt factor is the uh, very important factor in this equation because the this depends on the orientation of the plane and slip direction. So this defines the resolved shear stress for that any plane or direction. So we so if a crystal is aligning aligned on the 111 plane in the 110 direction, so that will be one crystal. So in the polycrystal materials or bulk materials, we have many orientations for different planes. So by combining all these planes, one bulk polycrystal forms. So for that material, different slip directions and slip planes will be there. So in that condition, polycrystal, we define that as the yield stress. So for uh, bulk material, the critical value is yield stress, yield strength of the material. But for single crystal, we say as critical resolved shear stress, to CRSS. So this is equivalent to the yield strength for a single crystal. So, and cos phi and cos lambda we can calculate from the cross product of the tensile stress axis and the slip direction and slip plane. So we will calculate the sorry we will solve the first problem. So the first problem says a tensile stress of sigma 5 kPa is applied parallel to the 432 direction. So the tensile axis direction is 432 of a cubic crystal. Find the shear stress toy on the plane 11 bar 1 plane and the 0, 0, 1, 1 direction. So first we calculate the Schmidt factor for the loading axis and for with the slip plane and slip direction. So cos phi will be between 432 direct 432 cross product of 432 and plane 1 1 bar 1, and cos lambda will be cross product of 432 and slip direction 0 1 1. So we can calculate the cross product 4 into 1 plus 3 into 1 plus 2 into minus 1 divided square root of this and square root of square of this. So 4 square, 3 square plus 2 square multiplied by 1 square plus 1 square. Okay. So this will be cos lambda will be 4 into 0 plus 3 into 1 plus 2 into 1 divided square root of this same 4 square, 3 square plus 2 square multiplied by 0 plus 1 square plus 1 square. So this will be 4 into 0, 3 and 2 will be 5 divided square root of 16, 9, 25, 25 and 4, 29, and this will be root 2, and this will be 5 by root 29 root 2, and this will be 4 into minus 4, 3 and 7, minus 2 is 5, so 5 by, so sorry, this is 4 into 3, 4, 3 is 7 and 7 is 2 is 9. This is 9 and this is 5. This will be square root of 29 and square root of 3. So the resolved shear stress RSS will be sigma m, means cos lambda and cos phi. So the applied stress is 5 kPa, 5 into 10 raised to the power 3 Pascal, into 5 by square root of 29 square root 3 and 9 divided square root of 29 square root of 2. So by calculating this, we can obtain the resolved shear stress value in MPa, or KPa we can also define. So is it clear? Can we proceed to next question? Lambda is the angle between slip direction and loading axis. Yeah, this is the lambda. This is the loading axis and this is the slip direction. So cos lambda is between slip direction and loading axis. So this is this 432 and 011. So next question says a cubic crystal is subjected to a stress state sigma x 15 kPa, sigma y 0, sigma z 7.5 kPa, and the all shear stress are 0. where x is 100 direction, y is 010 direction, and z is 001 direction. What is the shear stress on the 11 bar 101 slip system? So we have in this figure we can see this is the 11 bar 1 plane, and in the sigma z direction we have 0.75 uh, Pascal force. In the x direction, we have 1.5x, and in the y direction, the applied shear stress is 0. So we need to calculate shear stress for this plane slip system. So we calculate one by one for the x direction and y direction. Then we will add that to achieve the total shear stress. So for the x direction, loading axis we have 100, and the slip system we have 11 bar 1 and 101. This is the slip plane and this is the loading axis. So we can calculate first the Schmidt factor cos phi and cos lambda. So M will be cos phi between the slip plane and loading axis. So 1 into 1 plus 0 plus 0 divided root 1 and root 3 multiply. So in the cos lambda loading axis and the slip direction. So this also be 1 into 1 plus 0 divided root 1 and root 2. So we can write it as 1 by root 6. So the sigma on the sorry, the resolved shear stress on the x direction will be uh, sigma x we have 1.5, 15 kPa. 1.5 is in megapascal. So 15 into 10 raised to power 3 kPa into cos phi and cos lambda will is 1 by root 6. So we can write as 1.5 by root 6 megapascal. 1.5. Yeah, yeah. Notice 15 Pascal. And for the z direction, we have stress of 7.5 kPa, 7.3 Pascal, and the slip direction is 001. Sorry, slip. This is the loading direction. Slip plane is 11 bar 1 and 101. So the Schmidt factor cos phi and cos lambda will be 001. So it's 0 plus 0 plus 1 into minus 1 divided root 1 and root 3 multiplied by 0 plus 0 plus 1 divided by root 1 and root 2. So this again will be minus 1 divided root 6. So the total z will be 7.5 into 10 raised to power 3 into Schmidt vector minus 1 by root 6. So this will be minus of 7.5 into 10 raised to power 3 by root 6 Pascal. So the total RSS will be tau x plus tau z. So this will be 15 into 10 raised to power 3 by root 6 minus 7.5 into 10 raised to power 3 divided root 6. So this will be 7.5 only. Root 6 Pascal. So if we have given a stress for the two directions, so we can calculate like this. Okay, so I we'll discuss the assignment questions. So the first question says that make the correct statement. So first statement says that CRSS means critical resolved shear stress is the minimum shear stress required to initiate slip in a crystal. So this is correct statement. And next is the CRSS depends on the crystallographic orientation of the slip system. So it is also correct because the crystallographic orientation only defines the critical resolve shear stress for a single crystal. So in a polycrystal, it will be a single grain. And next option is it says for a single crystal material, CRSS is termed as yield stress. Yeah, so this is also correct. Next is critical resolve shear stress is temperature independent. Yes, so it is also correct. Means it is defined. No, no, sorry. It is not temperature independent. It is dependent. It depends on the temperature. So all four options are correct. Critical shear stress is temperature. No, all means first three are correct and the third is wrong. It is temperature dependent. With increasing the temperature, the some more slip system means the plane and direction will activate on the high temperature, so the resolved shear stress will change at high temperature. Okay. So the first, second, and third option is correct. Second question says the yield stress is at its minimum when phi is the angle between tensile axis with the normal to the slip plane and lambda is the angle between tensile axis and the slip direction. So we have to find the which option is correct. Yeah, so we discussed that the resolved shear stress depends on the crystallographic orientation. So when the Schmidt vector value will be maximum, means so the required applied stress should will be less. Means like M is the cos phi and cos lambda. So this depend on the loading axis and slip system. So the angle between slip direction and slip normal also defines the required amount of tensile stress for the deformation. So if value of the Schmidt vector will be high, then the required means we can say that sigma into m. So if we say m will be high, then shear stress, result shear stress will be high. So the required amount of loading stress or applied stress it can decrease. So if we have high Schmidt vector, so with very little amount of applied stress, we can achieve the critical resolved shear stress condition and material can deform. So to increase the Schmidt factor, the angle for slip plane slip plane normal and the slip direction will be approximately equal to the uh, 45 degree. Then only the cos phi and cos lambda will give the maximum value. So phi and lambda should be equal to nearly equal to 45 degree. And if both are 45, so phi plus lambda we can say they are 90 degree. So we can get the different value also not equal to 45 degree. If they are the addition of this is 90 degrees, so we will achieve the maximum value of Schmidt factor. So we can go to the options like it says the slip planes are oriented close to 45 degree with respect to axis of loading. So this is correct option. Second is says Schmidt factor is maximum and 5 plus lambda should equal to 90 degrees. So this is also correct. And y and lambda should equal to 45 degree. So all four options are correct for this. So the yield stress will be minimum when these four conditions will satisfy. Next question. Say an FCC single crystal material with a critical resolved shear stress 60 MPa undergoes deformation under uniaxial tension. Determine the tensile stress required to initiate plastic deformation when the slip plane is 111 and the loading axis is 112. So in this question we have given CRSS value and the slip plane and loading axis. So we have to find the tensile stress required to initiate plastic deformation. So the loading axis is 112 and the slip plane is 111. So for this slip plane, the slip direction will be 0 bar 1 1. So first we calculate the Schmidt factor. This will be loading axis and the slip normal. So 1 into 1 plus divided root 1 square, 2 square, and multiplied by 1 into 0 plus 1 into minus 1 plus 2 into 1 divided is root 6 and root 1 square plus 0. So this will be 4 divided root 3, sorry, root 6 and root 3 and multiplied by 1 by root 6 and root 2. So this will be 4 by 6 root 6. So this is the Schmidt factor. So we have to calculate the uh, uh, applied tensile stress. So we know that the resolved shear stress is the sigma into m. So sigma will be CRSS divided Schmidt factor. So twice the CRSS we have given 60 MPa, 60 divided by 4 by 6 root 6. So this will be 60 into 6 root 6 by 4. So this will be equal to 220 MPa. So third option is correct. So next option, sorry, we're coming to the next question. So it says which of the following statements about Pulse-Nabarro stress are correct? So Pulse-Nabarro stress, so there is one relation between the CRSS and the Pulse-Nabarro stress. So Pulse-Nabarro, PN and the CRSS both represents the same quantity, means the minimum stress required to move dislocation through a perfect lattice. So both represents the lattice friction, and both depends on the crystal structure and also depends on the Berger vector also. Berger vector is the slip direction. But if we talk about the temperature, so the Pulse-Nabarro stress does not depend on temperature. It is calculated at 0 Kelvin. But the CRSS varies with temperature. So we can uh, find the correct statement from the given. So first option is correct, means it is the stress required to move this location. It depends on crystal structure and depends on Berger vector, and it increases with increase in temperature. So this is wrong. So A, B, and C option is correct. Next question, we have asked that two edge dislocations are in stable equilibrium when. So this is regarding the interaction of dislocations when they come near to each other. Means if one edge dislocation is come is here and the second dislocation is coming near to the second dislocation. So both dislocation have some stress field uh, in the it because we discuss about the stress field in the dislocations in previous lectures also. So both dislocation has a stress field. So because of stress fields of both dislocation, they feel some force when they reaches to the uh, reaches to each other. So both are of same sign. So when second dislocation comes near to this first dislocation, so because they have same sign, so the means positive edge dislocation, so they will repel each other. But if we have positive and negative edge dislocation, so they will attract each other and annihilate like this, but this will repel each other. So this is for the single slip glide plane. But if we have dislocation coming on to the at some height or different slip direction or slip plane, means the glide plane is different. So for positive edge dislocation, when they come next to each other, so also in that condition they feel some stress. So we can say this is the x direction between it, and this is the y direction. So when x equals to y means they have 45-degree angle. So in that condition, the stress will be higher. Means the second dislocation will uh, feel the ripple force from the first dislocation. But if it reaches just above the first dislocation, so then the uh, force applied on the second dislocation will decrease. So this is the stable configuration when two positive edge dislocation come next to each other with different glide plane. So this results into the uh, dislocation array. So this is the stable condition for same sign edge dislocation. But if they have opposite sign, means this or this, a positive edge and negative edge dislocation. So the stable condition for this will be just opposite from the previous condition. So at 45-degree angle, they will be stable, and when it comes near, so they will repel each other. So the stable condition for this means negative opposite side sign edge dislocation will be this type. So all dislocation having 45-degree angle, then they are stable. And for the screw dislocation, means the two screw dislocations are these. So they also feel some force. So because screw dislocations can cross slip, so the force on that will be uh, lesser than the edge screw, sorry, edge dislocations. So in the lecture videos, the force applied uh, from the first dislocation to on the second dislocation is also calculated. So we'll just discuss the problems regarding the means the force equation for the edge and screw dislocation. So for the fifth question, this information is sufficient. So this in question we have asked that two edge dislocation are in stable equilibrium when they are stacked one below the other for the same sign dislocation. So this means the first option is correct. The same sign dislocation will make a stack array. And they are at positions x equals to plus minus y for the same sign dislocation. So this is wrong. They are far from each other for same sign dislocation. So in this option we have not mentioned the glide plane, means the glide plane is same or not. So this fourth option, it says that they are at position x equals to plus minus y for the opposite sign dislocation. Yeah, so for the opposite sign dislocation, the x plus minus y uh, will be stable equilibrium positions. So the first option and last option is correct. For the same sign dislocation, they will make array, and for opposite sign dislocation, this type of configuration they make. Okay, so we'll discuss the problems regarding the force. So we in this sixth question we have asked that two parallel and straight screw dislocation lie in a grain of nickel with a grain size about 40 micrometer. So 40 micrometer is given the length of dislocation. So if distance between the dislocation is 1000 angstrom, shear modulus 30 GPa, and B is the Berger vector 2 angstrom. So evaluate the total force on each dislocation if dislocation is of opposite sign. So for screw dislocation of opposite sign, the force formula is GB square by 2 pi 1 by x. So this Fx is the force per unit length. So we have given length is 40 micrometer, G is 30 GPa, B is 2 angstrom, and X is the 1000 angstrom. So we calculate from this. So G is the 30 GPa, B is 2 angstrom, 2 into 10 raised to power minus 10 square divided 2 pi. X is the 1000 angstrom. So this is the force per length. But we require total force. So the total force will be Fx into L. So when we multiply this value from the 40 micron, so we can, so we'll get the total force of the 7.6 into 10 raised to power minus 8 Newton, because Pascal is Newton per meter square. So when you calculate the unit for this, so you will achieve the Newton. So second option is correct for this. So the force, this force formula is derived in the uh, week 8 lectures. Okay, so we will go to the next question. So in the seventh question, we have asked that evaluate the force per unit length between two parallel edge dislocations of opposite sign lying on same plane. Given that the Poisson's ratio is 0.3, shear modulus 40 GP and Berger vector is 3 angstrom, and distance between dislocation is 1200 angstrom. So for edge dislocation, the force per unit length Fx will be GB square by 2 pi 1 minus nu into 1 by x. So we have given all values. G is 40 GPa, 40 into 10 to the power 9 into B Berger vector is 3 into 10 raised to the power minus 10 square divided 2 pi 1 minus Poisson's ratio is 0.3 into the distance is 1200 angstrom. So this will give the 6.82 into 10 raised to the power minus 3 Newton per meter. So the second option is correct for this. Next question we have asked. So this is the some other concept question. So we have asked that a cylindrical rod having diameter 150 nanometer, shear modulus 200 GP and Poisson's ratio zero point 0.5 and B is 3 angstrom. Find out the cell thickness up to which there is no whiskers for lattice resistance 1.5 Newton per meter. So whiskers we say which have no dislocation means simple very micrometer or nanometer level rods. Nanometer or micrometer rods having no dislocations. So how whiskers are formed? Because means if we have some material, so this, so we have some dislocation at this position. So this dislocation feels some surface force, uh, so that surface, because of that image force, this dislocation attract to the surface and and annihilate at the surface. So when this, to calculate that image force, we consider that some imaginary dislocation is sitting of the opposite sign is sitting at the same distance from this surface in the opposite direction. So this is x direction and this is also x direction. So both dislocations at same distance from the surface and they are of opposite sign. So because we discussed the interaction between dislocation, so the dislocation which is outside this attracts the dislocation inside of this and it will come annihilate at the uh, surface of this material. So this imaginary force we call it as yeah. So this imaginary force is uh, uh, determining means contributes to the formation of whiskers. Means if the distance is very less, This phenomena generally happens for very small length scale, means generally few nanometers. So if we have material with very small diameter, so that is to all dislocation in that region will come out and annihilate at the surface, so that material will become free of dislocations. And as the any material is free of dislocation, so the strength of that material will increase very high. So whiskers are known for the very high strength. So this is for the that small scale. But if we have bulk material, means greater than required uh, diameter, so for only some amount of so only dislocations which are near to the surface will annihilate at surface and make this region free of dislocation. So from the both side, the dislocation uh, are attracting to the surface and annihilating. So this region will be dislocation free. So the imaginary force formula is calculated to the from the lattice friction force, means the dislocation will coming to the surface. So this force is given as Fx GB square divided 4 pi 1 minus nu into T. T is the thickness of this region. So this Fx is generally equal to the lattice resistance of the material or of the crystal. So we have given all values, just we need to calculate this uh, distance or thickness of the material up to which no whiskers will be there. So we means GB square by 4 pi 1 minus nu into T will be equal to lattice friction we have given 1.5 Newton per meter. So thickness we can calculate GB square 200 to 10 raised to power 10. B is the Berger vector 3 angstrom divided 4 pi 1 minus Poisson's ratio is 0.5 into lattice resistance 1.5 Newton meter. So by calculating this, we so in this question the answers are given 1 point, but the correct answer is so when we'll calculate this, so we get the 19 angstrom. So in this question, the options are given correct. Some uh, typo error in that. So the correct option is 19 angstrom when we calculate from this. So you can cross check also from this formula. So we will get the 19 angstrom thickness. Okay, so we'll go to the next question. So, in ninth question, we have to mark the correct statement. So, yeah, so this imaginary force is true for both edge dislocation and screw dislocation. In screw dislocation, there will also be some imaginary force. So, we have given that a right hand screw dislocation at -x nearest a free surface generated left hand screw at positive x to satisfy the stress-free boundary condition. So it is correct, means right hand screw dislocation will generate left hand screw dislocation. And the second option say a left hand screw dislocation near a free surface generated left hand screw. So it is wrong. Say third option say a left hand screw dislocation at -x near a free surface generate a right hand screw. So this is also correct, means left hand screw make the right hand screw dislocation. And the fourth option is also correct. Sorry, incorrect. It because they are saying both right and hand is true. So first and third option is correct. Next question we go to. So in this also mark the correct statement regarding the image force. So image force on dislocation arises due to interaction with the free surface. Yeah, so this is correct because the interaction with free surface results in the image force. If image force is greater than lattice resistance, then dislocation near the surface move towards the free surface spontaneously. Yes, so this is also correct. Means if image force is higher than the lattice resistance, then the dislocation uh, will move to the free surface very easily. On so third option say only screw dislocation near the surface experience image force. No, both experience mean screw and edge both experience the image force. So both screw as well as edge dislocation near the surface experience image force. So fourth option is also correct. So we'll can discuss some more questions. So these questions are for the recent assignment for the week 8 lectures. So these are more or less similar to the previous questions. So in this we have asked make the correct statement. So CRSS is the minimum shear stress required to initiate slip in a crystal. So this is correct. CRSS does not depend on crystallographic orientation. This is wrong. It depends on crystallographic orientation. For a single crystal material, CRSS is termed as yield stress. Yes, so this is correct. And increasing temperature generally increase CRSS. No, with increasing temperature, CRSS decreases. So only A and C option is correct. Second question say reserve shear stress toy or negative slip system is maximum when. So we discussed just now that the 45-degree makes the Schmidt factor maximum. The Schmidt factor should be maximum and the 5 plus lambda should be equal to 90 degree. So first 1, 2 and 3 is correct. Mm. Third option we have asked that we have to calculate same as the only this the loading axis is different. So we have given CRSS value and slip plane. So we have to calculate the applied tensile stress. So loading axis is 110 and the slip plane is 111. So for this, the slip direction will be 0, 0, 1, bar 1. So first we have to calculate Schmidt factor, cos phi and cos lambda. So this will be 1 into 1 plus 1 into 1 plus 0 divided root 2 root 3, and here 1 into 0 plus 1 plus 0 into minus 1 divided root 2 and root. So this will be 1, 1, 2, 2 by root 6 into 1 by 2. So this will be 1 by root 6. So the applied stress will be dou by m. And this will be 60 by 1 by root 6. It's 60 root 6. So the answer will be 147 ampere. So option is good. Next question says, so it is the same as previous. Which of the following statement regarding personal stress are correct? So can you tell which option is correct? Option 1 is correct. Uh, it is multiple choice question, so some more option are correct. The personal stress as it depends on the crystallographic orientation. So for FCC and BCC, the crystallographic orientations are different. So the generally, yeah, option 3 is incorrect. It depends on the Berger vector, and it is independent of the temperature also. So the third and fourth option is incorrect, and first and second option is correct. Means for FCC crystal, it is lower compared to BCC crystal. Means BCC crystals are stronger than FCC. So first and second is correct. Fifth question says two edge dislocations are said to be in stable equilibrium when. So can you tell which option is correct for the fifth question? Okay. Yes, so for same sign dislocation, the x equals to plus minus y is unstable, and for same sign, and for opposite sign dislocation, this x equals to plus minus y is stable. Means this. So this is the plus y plus minus x, means x or y equal at in all four directions. Means making 45 degree angle. So the fourth option is correct. They are located at position x equals to plus minus y and have opposite sign. So for opposite sign dislocation, 45-degree angle is the stable condition. Okay, so then go to next question. Two parallel straight screw dislocation lies inside a grain of nickel with a grain size of about 50 micrometer. So the separation between the dislocation is 1200 angstrom. Shear modulus 35 GPa, Berger vector 2.5 angstrom. So evaluate the magnitude of force acting on each dislocation if they are of opposite sign. So Fx equals to for we have asked for screw dislocation. So GB square by 2 pi into 1 by x into L. So G is 35 10 raised to power 9 into 2.5 into 10 raised to power minus 10 square divided 2 pi. X is 1200 angstrom and L is the 50 micrometer. So we can calculate the answer from this formula. So in this question also, I'm getting around 14.5 into 10 raised to power 8 Newton, but this option is not given in this 4 10 raised to power minus 8. So you can also cross check whether it is correct or not because I calculated it many times, but still I'm getting 14.5. Next question. Good. Determine the force per unit length between two parallel edge dislocation of opposite sign located in the same slip plane, given that Poisson's ratio 0.3, modulus 40 GPa, Berger vector 3 angstrom, and distance is 1200 angstrom. Yes, so the force Fx will be Gb square 2 pi 1 minus nu by 1 by x. 1200 angstrom. So from this, the correct answer will be 6.82 into 10 raised to power minus 3 Newton per meter. So the second option is correct from this. Eighth question, it is that same again for the image force. A cylindrical rod having diameter 150 nanometer, shear modulus 200 GPa, and Poisson's ratio 0.5, and magnitude of Berger vector 3 angstrom. So we have to find the thickness up to which no whiskers for lattice resistance, 1.5 Newton per meter. So that will be GB square by 2 pi 1 minus nu. Sorry, it is 4 pi into T equals to this 1.5 Newton per meter. So in which we have to find the thickness. This. So we'll get 19 angstrom from this. So the second option is correct. Two more questions. So in the ninth question, we have to correct the mark the correct statement. So it is also same as previous, means a right hand screw dislocation is located near a surface. Determine the type of image dislocation at plus x to satisfy the stress-free boundary condition. So a right hand screw dislocation create a left hand screw image. So this is correct. Left hand screw create left hand. So this is wrong. Left hand screw dislocation create a right hand screw image. This is correct. And right hand screw. This is wrong. So A and C option is correct. 10th question say a screw dislocation moves near a free surface. Which of the following effects are correct? So the image dislocation exerts an attractive force on the original dislocation, and the interaction depends on the sign of dislocation. Yes, so this is also correct. Means when they are of opposite sign, then only they will attract each other. Yeah, when we'll get the admit card in allotted center for the exam. Maybe by the starting of April, you will get the admit card. Okay. So, do you have any doubt for today's session? Yes. Maybe I will recheck it. Exam date, I will recheck. Okay. So you just focus on the means assignment questions. Means the questions will be similar to these in the class only, and the some extra questions which I discuss in starting of the class is also uh, you can also go through. Means I discuss these in all uh, weeks, so this you will understand more about these problems from this, and you can go to the okay. Okay, then thank you. We'll meet in the next class. No, just I was saying that you can go if you have any doubt, you can go take help from the textbook also mentioned in the course, and the means I'm discussing these problems from the textbook only. So means these questions are sufficient for the exam. Okay. Yeah, horse food. Okay, thank you.